Hello everyone. Today we're going to talk about the first part of Chapter 11, which is correlations. And next week is our last week of learning new material. That'll be the second part of Chapter 11, which is regression. So we're on our last chapter, which is very exciting. So we'll start with correlation. So correlations is a measure that describes the relationship between two variables. And when we say we're looking at a relationship between the variables, a relationship means that you can predict when one variable changes, you have a pretty good prediction about what's going to happen to the other variable. Both variables must be on a continuous or numeric scale. That makes this chapter, Chapter 11, with correlation and regression, different from what we've done up until now. Up until now, we've had an independent variable that was categorical groups. We were comparing two groups in the cases of t-tests, one group who gets some kind of treatment, one group who doesn't get some kind of treatment, on a dependent variable like a depression inventory or a IQ test or something like that. But we were comparing two groups, or in the case of ANOVA, we were comparing three groups. Our independent variable was categorical, but now we were looking at three groups and comparing them. For correlation, your independent variable is a number variable as well. So it might be something like using hours of sleep, and so we would ask people how many hours of sleep they had each night, and it could be anywhere from 0 to, 12, a number, and using that number to predict, maybe happiness levels, how happy someone is. Does hours of sleep correlate with happiness? In that case, both of the scales are numeric or continuous. So the correlation coefficient we're going to talk about first is a statistic that quantifies the relationship between the two variables. Your correlation can be either positive or negative, and it falls between -1 and +1. That's -1 is the lowest you can get for a correlation coefficient, +1 is the highest, and it's typically a decimal of some kind. The statistic that we use is called a Pearson product moment correlation coefficient. That's a long name. It's represented by a lowercase r, as you see here. So we've already looked at z-score, z's, t's for t-tests, f we used for ANOVA, and r is the symbol for a correlation coefficient. And when you run a correlation in SPSS, you'll get an R, and there are two components of this statistic. The sign, it'll either be positive or negative, which will tell us the direction of the relationship. And then the size, so the kind of absolute value of the correlation, which ranges from 0 to 1, and that tells us something about the strength of the relationship. A correlation of 0, if you have an R equals 0, that means no relationship. So we're going to talk about all the sign and the size right now so you understand how to interpret a correlation coefficient. Starting first with just direction, and that's looking at just, is the correlation coefficient that SPSS gives you, is it a positive number or a negative number? So totally ignoring the actual number, all you're looking at is it positive or negative? If it's positive, we have a positive correlation. If it's negative, we have a negative correlation. And we're going to talk about these two special cases of a curvilinear relationship or no relationship as well. So we'll start with a positive correlation. So when your correlation is positive, and it doesn't matter, again, what the number is, as long as it's a positive number, what we mean is that the variables tend to move in the same direction. Meaning when one variable goes up, the other variable typically goes up. When one variable goes down, the other variable typically goes down. If someone is above average on one variable, in a positive correlation, it means that they tend to be above average on the other variable as well. And if someone is below average on one of the variables, they tend to be below average on the other as well. So here's some examples. Here's a correlation between SAT score and GPA. Okay, so we've got our SAT scores down here on the x-axis. We've got GPA up here on the y-axis. This is a scatter plot, and each dot on your scatter plot represents one case. In this case, it's one person. So in this case, let's say we've got someone who scored a 900 on the SAT, and their GPA, I don't know, is about a 2.3. And this person, this is someone who got like a 1350 on the SAT, and their GPA is about a 3.7. So each of these people represent a case. And what this is showing us is that when people tended to score lower on the SAT, they also tended to score lower on GPA. And as people scored higher on SAT, so these people over here in the 13 and 1400s, they tended to have higher GPAs. So this is a positive correlation. And a positive correlation is represented in a scatter plot by a line going upwards like this, slanting upwards from left to right. You can see how it's sort of doing that. That would let you know visually you're looking at a positive correlation. Another example here, years of education and salary. Again, here's a scatter plot where each of these points represents a single case. Sorry about that. And we've got people who tended to have low years of education, 9, 10, 12 years of education, tended to make lower hourly salaries, right? Here's someone with like 9 years of education making $5 an hour, which I don't think is even legal, but this is made up data. And then as people have higher and higher years of education, right, 12 would be a high school graduate, 13, 1 year of college, 14, so these are people who have gone on to graduate school. They have more years of education, they're also making more money per hour. Again, the dots are kind of going in this upward slanting line from left to right, and so we have a positive correlation. Okay, if the sign of your correlation in SPSS is negative, doesn't matter what the number is, just so long as it's a negative number, then we have a negative or an inverse correlation. So when the correlation is negative, and this is a little bit of brain gymnastics, the variables tend to move in opposite directions. So what does that mean? When one variable goes up, the other tends to go down. And when one variable goes down, the other tends to go up. If someone is above average on one variable, they tend to be below average on the other. And if they're below average on one, they tend to be above average on the other. So these two variables work inversely, or opposite. Here's an example of a negative correlation. This is the proportion of homework somebody copies during the semester of a class. So from 0% to 1 or 100% of homework copied. And this is their final exam grade. They standardized it where 0, this is a z-score, 0 is the mean, any positive score is above the mean, and negative scores are below the mean. So what do we have here? The less homework people copy, the higher their grades tend to be. And the more homework students tend to copy, the lower their grades tend to be. So this is a negative or inverse correlation. When you're low on one variable, like low on proportion of homework copied, you're higher on the other one, final exam grade. And when you're higher on this variable of proportion of homework copied, you tend to be lower on final exam grade. And in a scatter plot, this is a scatter plot with a lot of points, but you generally will see a downward sloping line from left to right. This means a negative correlation. All right, two special cases. One is called a curvilinear relationship. This is when increases in one variable are associated with both increases and decreases of the other variable. This is when the relationship looks more like a curve. It can look like a upside down U, like we have here. It can look like a U-shaped curve, the opposite of this, or some other curvy function. And this is often the case with when we're looking at human behaviors. Up until now, our positive and negative correlations, we're talking about how these variables are related in terms of a straight line. And humans are often a lot more complicated than that. So our behaviors are often related in more complicated ways. This is a relationship between anxiety and test performance. This is a curvilinear relationship. It's actually a true curvilinear relationship, and probably one of the most famous curvilinear relationships in psychology, that suggests that people with very, very low levels of anxiety tend to perform pretty low on tests. Why might that be? Well, people who have very, very low anxiety don't really care about the test. And so they think, oh, I'm not worried about it. I have a test coming up, and who cares? I'm going to go out with my friends or see a movie or play my video games. Doesn't really matter. And then they end up not doing very well on the test. We also find that people who have very, very high levels of anxiety tend not to perform well on tests as well, right? And these are people who have test anxiety, who get in the classroom and freeze, and they can't think, and they can't get their answers out, and they are so anxious they don't perform well. But it's that these moderate levels of anxiety, people who have a moderate level of anxiety tend to perform the best on tests, right? And you can imagine these are people who think, yeah, I have a big test coming up. I'm kind of nervous about it. I'm going to study instead of going out with my friends or seeing a movie. I'm going to try to get a good night's sleep and eat a good breakfast and then come to class and take my test, and they tend to do the best. And so this is showing that as you increase on one variable, like increases in anxiety here, those are associated with increases in the other variable. We get increases in test performance, and then when we get to a certain point, we also now get decreases in test performance. So this would be a curvilinear relationship. What's important about this is next week I'm going to show you how to graph your data. You always want to graph your data first to see what it is you're looking at. Are you looking at data that are kind of following a line, and so we know we have a linear relationship? Or do you have something that's curved like this? If you did graph your data and had a curvilinear relationship, you would need to do a different type of correlation coefficient, not the Pearson R. It's beyond this class, but nonetheless, it's important to be aware that you might see data that looks like this. Lastly, you might have variables that have absolutely no relationship with each other at all. Maybe you thought they would, but they aren't. And your scatter plot looks like this, a very random random display of the dots all over your scatter plot. And this might be something, if our independent variable was shoe size, and our dependent variable was IQ. These two variables are not related at all, shoe size and IQ, and it would show us here that someone could have a very small shoe size and have a low IQ, or they could have a small shoe size and have a high IQ, or they could have a large shoe size and have a low IQ, or a large shoe size and have a high IQ. There is no relationship. And this would be a correlation coefficient, an R of 0, or close to it. Okay, so just to reiterate, particularly positive and negative correlations. Positive correlations, when you graph your data, generally follow this upward sloping trend from left to right, which would be something like the relationship here between temperature and amount of beer sold, that when it's very cold outside, we tend not to sell as much beer. And when it gets warmer outside, more beer is being sold. So when you're low on one of the variables, we're low on the other. And when you're high on one of the variables, you also tend to be high on the other. This is a positive correlation. And then a negative correlation here, remember, would be your dots look at like this downward sloping line from left to right. And here's our relationship between coffee sales and temperature. So temperature again on the x-axis, coffee sold on the y-axis, and these in a negative correlation, the variables move opposite each other. So when we're very low on temperature, we're high on coffee sales. Many cups of coffee are sold. And when temperature gets higher, high on the temperature scale here, then less coffee is sold, right? So these two work in opposite directions. This is a negative correlation. Okay, that's all that information that you get just from looking at the sign. Is the sign of the correlation positive or negative? Now let's look at the strength. How strongly or weakly are the variables related? So remember, this goes from -1 to +1, with 0 being no correlation at all. A correlation of -1, this would be a perfect negative correlation. Correlation of +1, this would be a perfect positive correlation. Those are the strongest. The closer your decimal is to 0, the weaker your correlation is. And the closer your correlation coefficient is to 1 or to -1, the stronger your correlation between the variables are. In terms of interpreting the size of a correlation, here is a guideline that a small correlation is about 0.1, medium about 0.3, large 0.5 and higher. So here's an example of a perfect positive correlation. When we say perfect positive correlation, it means every single dot falls exactly on this line. There is no deviation. There's no dots that fall off of this line. Every single one falls on this line. That's what a perfect positive correlation would look like if it was graphed. In this case, we've got number of absences and exam grade. This is showing us that people who have a low number of absences have low exam grades, and people who have a high number of absences tend to have high exam grades. Do you see anything wrong with this data that's, again, made up? Well, number one, it doesn't really make a lot of sense, right? That people who have lower absences would have lower test grades, and higher number of absences would have higher test grades. That doesn't make sense. That you would think, what direction would that correlation typically go in? Hopefully you're thinking negative, right? The more absences, the lower the test grade, and vice versa. And so, again, this is not a real perfect positive correlation. And this would say that every single student follows this exact pathway, that every time a student misses 2 classes, they will always get a 40 on the exam. There's no variability there. Nobody who has 2 absences would fall off this line, off this dot of 40. They would never get a 20 or never get an 80, and you know that that doesn't make really any sense. We almost never see perfect, well, we probably never see perfect correlations in psychology because human behavior is just too complicated. Now here's a perfect negative correlation, number of absences and exam grade. So this is looking like a negative correlation. Again, the dots are this downward sloping line. And this is negative, showing that people who have 0 absences get a 100 on the test. And people who have a lot of absences, like 8, get a 20% on the test. So this is more realistic in that this negative correlation probably makes more sense than positive. But would it be a perfect negative correlation between absences and exam grade? Meaning that any time a student missed 0 classes, they always get 100% on the test? You know that doesn't really make a lot of sense, right? You might have been to a class where you've never missed any classes and maybe not gotten 100% on the exam. There's variability in this. And so this would be a correlation coefficient of -1, a perfect negative correlation. So here's the positive one, right? R equals positive 1. This is a perfect positive correlation. The dots are all on this line and there's no variation. Here's a perfect negative correlation. The dots are all on this line, downward sloping line, and there's no variation. Here's our correlation coefficient of 0, meaning there's no relationship here. But down here is where it gets a little bit more realistic in terms of actual data. This is a correlation of 0.80. So it's a positive correlation, and you see that this is an upward sloping line, right? That if you're low on this variable of x, whatever it is, you also tend to be low on y, and people who are high on this variable of x also tend to be high on the variable of y. But it's not perfect, right? The dots don't fall exactly on the line like this. There's a little bit of variability. It's still pretty good. This is a very nice, strong correlation of 0.80. It's close to 1. It's over that 0.50, which was the scale that I had showed you earlier in terms of interpreting. This is a very strong correlation. Not perfect, but strong. Here's a correlation coefficient of 0.3. So again, it's a positive correlation. Generally, you see this upward trend that as people are lower on one variable, they're lower on the other, and as they get higher on one variable, they are also higher on the other. But there's more variability, right? People who get a 10 on this variable of x, whatever it is, are scoring between a 10 and a 30 on y. There's some variability there. But nobody who got a 10 is scoring higher than 30, right? And as you go up, like a score of 50, now you've got people who are scoring higher on this other variable, and nobody's down here. So this is a moderate correlation between the variables. And lastly, this R of negative 0.20. Here's a negative sign. We've got a negative correlation, and you can see generally this downward sloping trend here, where when people are lower on this variable of x, they tend to be higher on y, and higher on this variable of y, higher on this variable of x, they tend to be lower on the variable of y. Sort of have this downward trajectory. But again, there's a lot of variability. This is much more like what actual psychology data looks like, because it's hard to get perfect predictions for anything. Like if this was test grade, we were trying to predict someone's test grade, even by hours of studying, right? People who studied less for the test, oh no, let's think about this. It's a negative correlation. Well, I'll look over here. Hours of studying and test grade, right, for this correlation of 0.3. People who study less for the test tend to get lower grades, but not everyone, right? You know, there are some people who don't study very much, and they still do pretty well. And same here, when people study more, they tend to do better, but not always. Sometimes people who study a lot get kind of an average grade. And so that's more realistic when it comes to predicting human behavior, is that we have a lot of variability. Very rarely do we have something even that looks as close as this, like this 0.80. All right, so check your learning. Which correlation is stronger? The correlation of 0.25 or negative 0.74? Which one is stronger? Hopefully you're going to say negative 0.74. Remember, for the strength of a correlation, it doesn't matter if the number is positive or negative. You just want to see which one is closer to 1, and 0.74 is closer to 1, closer to a perfect correlation, than 0.25. This is a weaker correlation. All right, limits of correlation. You have to remember that correlation does not mean causation. When we've got two variables that are correlated, it doesn't mean that one causes the other to happen. It could be that one variable causes a change in the other one. There's also a possibility of reverse causation, meaning the second variable is actually causing a change in the first, or that a third variable is responsible for the correlation totally. And you probably learned a little bit about this in statistics. You'll learn more about this in a research methods class, but just be sure when you see a correlation, you're saying, okay, there is some relationship there, but I still yet don't know which variable causes a change in the other variable. All we can say is the variables are associated or there's a relationship, but we can't say anything about cause and effect when you do a correlation. All right, so the Pearson correlation coefficient, that's the statistic that quantifies the linear relationship between two scale or numeric variables, symbolized by R when we're talking about sample data, and in the population, it's the letter rho, which looks like this curvy P. I'll show you on the next slide. So just like we have the symbol of capital M or X bar, if we're talking about mean in a sample, and if we're talking about the mean of a population, we use the Greek letter mu. For the Pearson correlation coefficient, we're using the Greek letter rho when it's a population that we're talking about. So the Pearson correlation coefficient can be used as a descriptive statistic, just like what we did. Basically, you can interpret that R and say something about your sample data, that there's a positive or negative correlation and how strong it is. But it can also be used as an inferential statistic, which is what we're going to talk about now, meaning we can do a hypothesis test on that correlation coefficient to say, do we know what the relationship is in our sample, but do we think that relationship would hold up in the population? So in this case, we're looking at our first problem is skipping class related to your statistics exam grade. We have 10 students. We have how many absences and their exam grade. So student 1 missed 4 classes and got an 82 on the exam. Student 2 missed 2 classes and got a 98. Student 9 missed 7 classes and got a 50. Okay, so there's our data. Remember, for a correlation, you need 2 variables, which we have here, and they're both on a numeric scale. Absences is on a number scale, this case ranging from 0 to 8, and exam grade is also on a number scale. So we know we can do a correlation here. Always start with a scatter plot. In this class, it will be important, and we're going to learn about how to make a scatter plot next class, but I'll do one here for you. So here's number of absences and exam grade. And you can see this it's kind of this general downward sloping line. So what kind of correlation do you think we're expecting here, positive or negative? Well, it should be a negative correlation. And let's go through the steps. So state the null and research hypothesis. For a correlation, the null hypothesis is always rho equals 0. Meaning the correlation in the population, that's the correlation coefficient symbol in the population, is equal to 0, meaning there's no correlation, right? The null hypothesis is always the hypothesis of no relationship or no effect, and that's the case here. So we're saying there's no correlation between number of absences and exam grade. The research hypothesis is always that rho is not equal to 0. Suggesting that there is a correlation between number of absences and exam grade. So these symbols here, H sub O as rho equals 0, and H sub 1, that rho is not equal to 0, these are always your hypotheses for a correlation, for any correlation that you do. So these are always your hypotheses here. Then you run your descriptive analysis and your inferential analysis in SPSS, and I will show you how to do that on the next lecture, or the SPSS lecture. But you get something that looks like this. So for absences in our group, we had mean absences of 3.4 with the standard deviation of 2.5, 10 people. And exam grade, the average was 76. Here's the standard deviation and also 10 people. Then you'll get this correlation matrix looking at absences and exam grades. And again, a little bit like the post hoc testing is in ANOVA, you get some redundant information. So first of all, SPSS computes the correlation between absences and absences. It's a perfect correlation of 1. but it's useless. We don't need it. It's, you can ignore it. It also looks at the correlation between exam grade and exam grade. Again, that is a perfect correlation, and it's useless, so we ignore that. And then you've got your correlation here between absences and exam grade. Here's your correlation of negative 0.851. So this is the R is negative 0.851. So it's a negative correlation because we have this negative sign. And 0.85, well, that's a very strong correlation. That's pretty close to -1. And again, you get the same redundant information here. This is looking at the correlation between exam grade and absences, which is the same as the correlation between absences and exam grade. You can ignore it. Okay, so you just need to look at one of these boxes. Here's your correlation coefficient, your R. Here's your significance, two-tailed 0.002. Just like in all of our other testing, we'll compare this to an alpha level of, let's say, 0.05. So this significance level must be less than 0.05 for it to be statistically significant. And if this is greater than 0.05, then it is not statistically significant. And this is saying we have 10 pairs of data, 10 data points. So making our statistical and substantive conclusions, statistically we're going to reject the null because our obtained P of 0.002, remember, came right from here, our obtained P, is less than the critical P of 0.05. Substantively, you want to say what this means in words, and you're basically describing this negative or positive correlation. Since we have a negative correlation, what do we know? As number of absences increase, statistic exam grades decrease. That's a negative correlation. As this variable goes up, the other one goes down. All right, so that is the end of this lecture, and then go on to watch the SPSS lecture next to see how to run this in SPSS. Thank you.